Hello everybody. So in this video, I'm going to be going over how to solve first order linear differential equations. But before we get into like practice problems and whatnot, I kind of want to go over how to solve for the general solution of these types of problems. So that way when we get to the practice problems, we could just quickly do like plug and chug stuff. And I find it easier to look at the proof behind these general solutions, so that way when we get to the actual practice problems, it'd be more clear to look at. So not only can we just quickly plug and chug stuff, but it would also make sense to us. So yeah, let's just get right into it. So first thing that we want to do is get this dy dx on its own. And to do that, what we're going to be doing is dividing both sides by a of x. So that way when we do divide both sides, we get dy dx plus b of x over a of x y is equal to c of x over a of x. Now at this point, what we could do is make this problem simpler for us we're going to make this problem a bit simpler for us, pretty much. We're going to crunch it up. So this b of x over a of x, what we could do here is, okay, that's not dx. So this dy dx stays the same, but what we're going to do is that b of x over a of x, we're going to turn it into this new function p of x, because this is still in terms of x. So we're just going to say it's p of x just to like crunch it up a bit to make this look less complex. So we get this y. Same thing for this c of x over a of x. We're going to turn it into this new function q of x. Okay. So at this point, we're going to mess around with it again and multiply this by some term or by some function u of x. Now this function u of x is special. Right now we're just multiplying this whole thing by u of x, but we don't know what u of x is. However, we are going to be solving for it because it's going to be included in the general solution for y of x. So pretty much later, as you'll see, we need to solve for this in order to solve for y of x. So again, we're multiplying this by the general function u of x. So we get u of x dy dx plus u of x, then px y. Now we just get this whole thing. Now it does look like we made it worse by introducing this new function u of x. However, when we do this, we could do magic pretty much. So there's a few things that there's a few assumptions that we can make right now. So what we could do is that, notice how this term, so right now we're not even focusing on the right side of the equal sign, so completely block this out of your mind. Notice how on this term right here, we have u of x, the function itself, times the derivative of y with respect to x. Then on this part, we have u of x times this new function p of x. We don't know what it is. And we also left y on its own. So pretty much, if you're not able to see it now, this is pretty much a product rule. So we have d dx, then we have u of x times y. Again, you can kind of see this by on this left side right here, we took the derivative of y with respect to x and left u alone. And then for this part, we took the derivative of u of x. So it gave us this new function p of x, and we have the y left alone. And as for this right side, it stays the same. So we get u of x times q of x. But in order for this to be true, we now had to set, okay, sorry about that. There was a slight interruption. It's garbage day. So back to where we're at. So in order for this right here to be true, we need because the derivative of u of x happens to be u of x times p of x, that's a condition that has to be true in order for this to be true, pretty much. So we're gonna be left with, so right here I'm gonna write, we have du dx is equal to this, u of x times p of x. So now at this point, what we could do is just solve for u of x. So via separation of variables, we get on the left side 1 over u du is equal to p of x dx. And we can integrate both sides. When we integrate this left side, we get ln of u is equal, and on the right side, we're just keeping it the same because we don't know what p of x is. And then solving for u of x, we get u of x is equal to e to the power of p of x dx. So here is one condition that has to follow in order for this right here to be true. So now that we have that, we can continue on here solving for y. Again, we could solve it via separation of variables. So on the left side, we could get d of uxy is equal to u of x times q of x dx. Again, integrating both sides. On the left side, we just get left with u of x of y. Then it's going to be equal to this integral. We don't know what it is. We don't know what u of x is or q of x, so we're just going to be leaving it as it is. However, when we do integrate this, we're going to be getting a constant. So I'm going to introduce that constant right here. And solving for y of x, and yeah, y is a function of x because by the linear differential equation, dy d of x means that y is just a function of x. This is just an ordinary differential equation, so we could just say y of x. Then we get 1 over u of x. Okay, let me write this a bit more clear. So we get left with y of x is equal to 1 over u of x times the integral of u of x, q of x, dx plus c. And I probably should have kept consistent with the colors, but garbage truck interrupted me. But I'm just gonna leave it like that. So here we have the general solution for y of x when you're given a first order linear differential equation, where u of x has to be this right here. And yeah, we could just get into some practice problems right now. So here we have a first order linear differential equation, and we're just going to solve it in the same way that we did when we did the derivation for this. So again, we need to get dy dx on its own, and the way we do that is by dividing everything by 2 of x. When we do that, we get dy dx. When we divide this x by 2 of x, we get left with 1/2 y, and then on the right side, we just get left with x over 2. And at this point, we're going to be multiplying it by some function u of x. Again, right now at the moment, we don't know what u of x is, but we're just going to introduce it. So we get this u of x, and we get 1/2 y is equal to u of x. Then I'm just going to take the x out of this half, so 1/2 x. Okay. Now again, we're assuming this left side is just a product rule. So d dx of u of x times y. And by doing that, when we do that, we're assuming du dx, when we differentiate, when we take the derivative of u with respect to x, we're assuming that the solution is this part right here. So u of x times 1/2. And I'm just gonna skip the derivation of this, but we know that u of x is equal to e to the power of the integral of p of x dx. Or in this case, our p of x was the 1/2. Same for right here. We could just see that our p of x is just 1/2. So this becomes 1/2 dx. So our solution for u to the x is going to be e to the 1/2 x. Now this does make sense because when we take the derivative of this, we just get left with the 1/2 outside. So it would look something like this: 1/2 e to the 1/2 x, and e to the 1/2 x is just our u to the x. That's where we get this part right here. So it all comes together pretty much. And I'm just gonna write out the rest of this equation. Because we know what u to the x is, we could just substitute this in for that. I'm just gonna do that right now. So e to the 1/2 x y, then we just get e to the 1/2 x and 1/2 x. Okay, and now at this point we can just solve for y, doing the normal deriving stuff, except I'm just gonna skip to the point where we get the form of solving for y. So we get y to the x is equal to 1. Then right here would be 1/u to the x, but we know u to the x is e to the power of 1/2 x. So I'm just gonna write this as e to the negative 1/2 x right there. Then this would be the integral. When we solve for the solution, it was u of x times q of x. Our q of x in this case is this part right here. So I'm just gonna write is equal to q of x. So this part right here is our q of x. And there's our u of x. So we're gonna be taking the integral of e to the 1/2 x times 1/2 x dx plus our constant c. Okay, so now all we need to do is just solve for this integral. So I'm just gonna do Tabular's method, which is just integration by parts. I'm gonna take the derivative of 1/2 x. So that way, when we go all the way down, we just get 1/2 and then 0. And then I'm gonna take the integral of this part right here. So e to the 1/2 x. When we take the integral of that, we get 2e to the 1/2 x and 4e to the 1/2 x. And here we have our answer if we just go diagonally. So we get y to the x. Here is where we get our final answer now. Really, the only tricky part, once you know all this, is just solving for this integral, which our final answer now is gonna be, so we're multiplying these two terms. This 1/2 and 2 cancel out, so we're left with x e to the 1/2 x. Then we have our minus right here. We're multiplying all these three together. So pretty much for this first part, we just multiplied these three together, this plus this term and this term. Now we're multiplying this -1 times this 1/2 times that. So now we get left with minus 2e to the 1/2 x. Then we have our plus c. And that's our solution for this differential equation. So really, the only thing we did different that I didn't cover in this video was just this integration by parts. So everything else is just kind of the same. If you wanted to, you could have just jumped to this solution by the general solution for y to the x. But yeah, really the only thing different we did was just this integral right here. This next problem we could go through it a lot quicker. So yeah, just on to the next problem. So here we have another differential equation. However, this one's a bit less obvious when you look at it, that it's a first order linear differential equation. But by messing around with it, we could get it to be one. So what we could do here is subtract. We want to get y over x to the left side. So we're going to subtract both sides by y over x. When we do that, we get left with dy dx minus y over x is equal to 2x plus 1. Here we already have our q of x, here we have our q of x already. And right here, what we could do is, instead of writing it like that, what I like to do is put 1 over x times y. And instead of having the negative on the outside, we're going to have it on the inside right here. So now we know our p of x and our q of x. So here is the general solution for y of x for first order linear differential equation. So I'm just going to write out this part. So we know our q of x. And because we know our p of x, we could solve for our u of x. So our u of x is e to the power of the integral of p of x dx. And our p of x in this case is -1 over x. So this right here becomes -1/2, or not -1/2, sorry. It's going to be -1 over x, and I'd like to write that in blue right here as well. Okay. So when we solve for this, we get u to the x is equal to e to the power of -ln of x. By log rules, we could put this negative on the top right here. So it's x to the power of -1. So that way this e and this ln can cancel out. So now we get u of x is equal to x to -1. So here we have our u of x, here we have our q of x, and now we could just plug them in. So now y of x is going to be equal, because u of x is in the denominator, this is just going to be an x. Then we have the integral. Our u of x is just 1 over x, and our q of x is 2x plus 1. Okay. Now we just need to solve for the integral, and we get the answer. So when we solve for this integral, we get y, again, y of x is equal to x times, so solving for this integral, 2x times 1 over x is just 2, and the integral of that is just going to be 2 of x. And then 1 times 1 over x just gives us 1 over x, and the integral of 1 over x is just ln of x. Then the plus c. And here is our solution for this, for the first order linear differential equation. And yeah, it's quick as that, simple as that. And hopefully this video helped you guys out. And yeah, see ya.